Hey guys, I'm Injun.
I'm Crystal.
I'm Adeline.
I'm Jensen.
I'm Zulfat. I'm Shakin Rashraw.
And we are
Group 5.
And we are doing
Question
3.
So we'll be talking about the concepts of the magnetic flux and the magnetic induction in transformers.
This video will be explaining the setup and operation of the transformer.
And we'll also be talking about the back EMF and the energy issues in the transformers.
Lastly, we'll be talking about the application of transformer. So guys, let's get started.
Hey Crystal, what you doing?
Hi, I'm looking at transformers.
Oh, you mean the movie?
Nope. I mean the physics one.
Oh.
Do you know that transformers can be found everywhere and even in our phone chargers?
I didn't know that.
It looks like that. Let me explain to you the setup of a transformer. So this I got from the internet, and it's the one that we're so used to seeing. And this is from the physics lab. So this is the input current, which is this one. And from there, it goes to the primary coil. And the primary coil is the one down here. And this is the iron core, which is this big gold thing that you see here. And from there, this is your secondary coil, which is the one up here. And from the secondary coil, your current goes out to your load. And your load is like wherever you're charging, like your phone or your laptops. And that goes from here out here.
All right. Thanks, Crystal.
Welcome.
Hey guys, this is Lian and I'm going to be explaining about the operations of a transformer. By definition, a voltage transformer is a device that works on the principle of Faraday's law. So what it actually does is it steps up or steps down voltage. So, according to this charger over here, it says that its input voltage is 230 volts, where its output is only 3.7 volts. So as its input voltage is higher than its output voltage, this is clearly a step-down transformer. Okay, so now let me explain how a transformer works. So first, I'm going to be drawing the core of the transformer, which is usually made out of laminated iron to reduce eddy current. And on the left side, I'm going to be drawing 6 coils. And I'll be labeling them as number of primary coils. And on this side, I'll be drawing 3. And label them as secondary coil. So the secondary coil is usually connected to the load, such as your laptop or your phone charger. And on this side, it's connected to an AC source. So, you might be wondering, why AC? Why not DC current instead? Well, according to Faraday's law of magnetic induction, it states that whenever a conductor is placed in a very magnetic field, an electromotive force is produced. That's why, using an AC current, a very magnetic flux can be produced. For example, if the current is going this way, by using your right hand grip rule, you know that the direction of magnetic flux is going up. And if the current is going the other side, you know that it's going down. So, when an AC current is used, the current changes direction constantly, producing a constant change in magnetic flux throughout the whole core. This induces an EMF in the secondary coil. There you go, that's how a transformer works.
Now we'll be talking about back EMF in transformer. First off, we use Ohm's law, which is V equals to IR to calculate the voltage in a circuit, but it is not true for the first few milliseconds. As you apply voltage through a circuit, the voltage will build up the current gradually in the same direction. The building up of current will cause a change in magnetic field, and according to Lenz's law, the changing magnetic field will in turn produce an EMF that has a opposite direction to the applied EMF to counter the change in magnetic field. The back EMF, along with the magnetic field created by it, will disappear after the current flow is stable in a DC circuit. Next, in a transformer, an AC supply is used. It produces an oscillating current in the primary circuit, and the current produces an oscillating magnetic field. The magnetic field passes through both the primary and the secondary coil. According to Faraday's law, it will induce an EMF in both the circuit. The current is induced in the first circuit, but the second circuit is open, so there is no current flow in the second circuit. The change in current through primary coil induces an EMF that is of opposite direction to the applied voltage. As in, if the voltage is pointing up, the back EMF will be pointing down and vice versa. The magnitude of back EMF depends on the number of turns of coil. As a typical transformer has a large number of turns, its back EMF is also huge. In this diagram, the secondary circuit is closed and loaded with some resistance that allows current to flow through. Now, if you remember what I said in the previous slide, the changing current produces a magnetic field that passes through both coils. It will now induce a back EMF in primary coil and a EMF in the secondary coil. Since V back 1 and V2 are induced by the same change in magnetic field, they will point in the same direction. Thus, I2 is the opposite of I1. And the change of current I2 also produces an additional change in magnetic field in the core. Hence, another back EMF is induced in the primary coil. As you can see, the direction V back 2 is the opposite of V2. Thus, it is in the same direction as V application, which strengthens the net voltage. Well, this is the end of back EMF.
Okay guys, so in this part of the video, I'll be talking about the energy issues in a transformer. Nothing is perfect, so there will be bound to be several problems. And in this case, it is the energy issues found in the transformers. So one of the first issues I'll be talking about is the resistance of the coils. The primary and the secondary coils are both made of long and thin wires. As such, resistance will be present when the current flows. When there is resistance, the current in the flow cannot flow smoothly, which will form a traffic jam-like situation. This will generate heat, a form of energy converted from the electrical energy in the coils. And as heat is a form of energy that can be lost through radiation, the transformers will encounter energy loss through the form of radiation. So how do we solve this? Well, throughout the years, we've been using thicker or copper wires to reduce the resistance, and this can reduce the energy loss faced by the transformers. In the second issue, I'll be talking about the eddy currents in the iron core. In the primary core, the alternating current, or AC, will produce a changing magnetic flux in the soft iron core. This will cause an induced current to form in the soft iron core itself. But the core itself is not connected to any complete circuit. So where does or how does the current flow? Well, the current can only flow in the core itself. And this will create a loop or swirl of sorts, causing the eddy current. And as the current flows, it will eventually generate heat and cause energy loss through radiation, which is similar to the energy loss caused by resistance from previously mentioned. Now, how can we solve this? Well, we can laminate the soft iron core to reduce the eddy currents. As shown in the picture beside, the non-laminated core will have a larger eddy current flowing through the core itself, while the laminated core will have smaller eddy currents that are distributed through the laminated cores, and this will reduce the energy loss faced. The third issue is the magnetization or the demagnetization of the core. In the primary coil, the current will cause the soft core to become a magnet, an electromagnet more specifically, and the changing current of the alternating current will cause the magnetic flux of the core to change constantly. And they change constantly, the soft iron core needs to magnetize and demagnetize constantly, and this process requires energy. So when the magnet is magnetized and demagnetized to change the direction of the flux, energy will be used and will be lost for the process, and this will cause the energy of the current to not be able to transfer completely to the secondary coil. A way to solve this is to use the soft iron core, which can be magnetized and demagnetized easily, or using materials that can be magnetized easily for the core itself. And the final and fourth issue I'll be explaining is the leakage of the magnetic flux. The magnetic flux produced by the primary coil is not completely linked, or it is not in touch with the secondary coil. As such, the energy of the current can only be transferred through the flux itself, and some of the flux can be lost to the surroundings through the radiation. And as this happens, the energy from the current will be lost along with the flux itself. As such, there will be some loss of energy. To fix this, we can have the secondary coil on the top of the primary coil, or closer to the primary coil, to allow easier flow of energy. So in the next part of the video, we will be talking about the applications of the transformers itself.
Now, into a third point, we are going to talk about what are the applications of transformer in daily life. First and foremost, we are going to look into what are the role of a transformer in the transmission of electricity. First, electricity is generated from a power station. It will then be stepped up by a step-up transformer to increase its voltage. This is because as electricity is transmitted through a long distance, energy will be lost as a form of heat energy. To ensure that the electricity will reach the substation, the voltage is increased. Upon reaching the substation, it will then be stepped down by a stepped-out transformer before distributed to the consumer. The picture below shows how a typical electric system works. In short, the transmission of electricity can be summarized into a flowchart like this. Next, I will talk about the role of a transformer in metal manufacturing. Metal industry require a wide range of voltage for different manufacturing purposes. For high current, it is required for the melting of metal or the welding of metal. For low current, metal industry will use it during the cooling process of metals. So this is a picture showing how does a metal molten looks like.
Next, we have another application of transformer, which is the charger. Firstly, the function of a charger is to convert a high voltage AC current into low voltage DC. As voltage from socket are higher, a step-down transformer is used to lower the voltage for charging. This will prevent overload of electricity, which might lead to explosion. Transformers are used to control the voltage that enters the battery during the charging process in order to prevent any damages that can occur to the internal battery components. This is important because an unregulated voltage can result in high surges during charging of batteries. This picture shows the transformer component in a plug. Next, we have the audio transformer, which is the speaker. It is used for matching microphones to amplifier inputs. It also allowed the AC audio signal to reach the loudspeaker while preventing any direct current from the amplifier affecting the operation of the loudspeaker. Then, it provides an isolated external connection for the loudspeakers, thus improving safety. It also can match low input impedance of loudspeaker to high output impedance of amplifier, allowing maximum power to be transferred from the amplifier to the speaker. This diagram shows how an audio transformer works in a speaker.
Moving on, I'll be talking about the transformer modifications. One of the modifications that can be made is the limitation of the temperature rise. Lower temperature rise is achieved by incorporating a more robust core and winding configuration. When one is converting power from higher to lower voltage or vice versa, heat is generated through the transformer. Hence, to reduce the amount of heat produced, lower temperature rise transformers should be used. Less heat being generated could prolong the life of the equipment and be less of a burden on the facility cooling systems.
Secondly, another modification that can be done to reduce the energy wastages of a transformer is to replace the copper coils and iron cores of the basic transformer with semiconductor components and integrated circuit. This is because basic transformers tend to waste electricity even though there are no usages. With the upgraded version of transformer, the amount of current needed to supply to electric machinery will be reduced. Besides that, this version of transformer is also environmental friendly as they do not contain mineral oil, which is an insulation that can leak and pollute the environment.
Thanks for watching!
So if you like this video, please hit like and subscribe. Thank you, Mr. Alex. We love you.
Bye.
Bye.
Okay, that's all lah.
Chaka, you still in the frame, you know, after you say gel.
Yes,
Yeah.
Hi guys!
That's a nice group. Come back. They can't control it. Take two.
Okay,
Start.
do it.
We start.
3, 2, 1, start. Hi guys, this is group 5 and we are doing question 3. I am Mingjun.
I'm Crystal.
I'm Madeline.
I'm Jensen.
I'm Zone 5. What are you talking about? Hey, you say you want to do one turn, then you do this shit. That's already.
That's my turn.
Yeah.
Oh, okay. So we'll be talking about the concepts of the magnetic flux and magnetic induction in transformers.
And so this video will be explaining about the setup and the operation of a transformer.
Sorry.
Again.
Just continue.
And we'll be talking about the back EMF and the energy issues of the transformers.
Lastly, we'll be explaining about what is the application of a transformer. So guys, let's get started. What's the last one?
And last is
Okay.
Sorry, I keep forgetting that Madeline is the...
Should I stop?
Yeah, stop.
3 second rules, honey?
3 seconds.
Do you drop that?
No.
Are you sure? This is going on a video.
Really?
Bloopers.
How do I stop it?
Friends.
Say bye.
Oh, put this in the video. Put this in the video. No, just kidding.